Section 1.3 is titled Measuring Segments, but we're going to see that we're going to do a lot more than just measure in this section. Our first postulate is called the ruler postulate, and it's honestly not too important for what we're doing other than the fact that we're measuring up a ruler with what we call our coordinates on a line. So if I have points at A and B and I can match those up, I can line those up to what we call that coordinate on a ruler. Moving further on to trying to use that ruler postulate, we're going to use that to measure distances, just like you'd use a ruler to measure distances. And again, we're going to find those distances on a number line. It's going to look kind of scary because we're going to define that as the distance between 2 points by saying it's the absolute value of the difference of those two coordinates, written as the absolute value of something like coordinate A minus coordinate B as those two variables. The important thing to note here from this section, really, biggest thing to take away is the difference in notation, which might seem kind of slight. If I'm looking for the length of a segment, I'm going to call that something like AB. Notice there's no segment marking over the top. And if I'm calling that AB as a segment itself, that's the difference between calling something a segment or referring to its length. So if I'm referring to its length, I don't include that bar over the top. But either way, it looks, again, kind of scary by taking that absolute value of a difference to find a length. But it works a lot like how we measure on a ruler. If I'm looking for example, the length of ST, you guys might really just like count how far we're going over. That's a way to find the length, just like it would from before. If we're following the exact postulate, all I have to do is find the absolute value of the difference of those coordinates. Or really, you can, again, just think what's the length between those two. So if I'm trying to include that in the formula, the coordinate for S is -4, the coordinate for T is 8. If I find the difference between those, the difference is -12. But again, for lengths, we want those always to be positive. So all we've got to do is really figure out the difference between those two, make sure we use the positive value, and that positive value of the length is going to be 12. Trying a similar question, and again, this is a good place to pause the video and try to do that question yourself on that next number line. I'm just going to reveal the solutions, but move on pretty quickly because, again, works the same way as before. Find the difference between U and V. Make sure you use the positive difference instead of the negative, and that would be a difference of 4. Again, honestly, easier just to count if you have that ability as well. And same thing for SV. If I just count that distance, I know that that's a distance of 18 from one to the other. Or if I just think of that as the positive difference between those two, oops, sorry about that, that's going to be 18 as well. So moving on to the next part, which we're kind of going to call the segment addition postulate, is actually going to allow us to use some of our algebra here. If I use a segment addition postulate, we're essentially saying that if I add the first part of a segment with the part that's next to it, we're going to be given this length of the entire segment. So let's say, for example, it's kind of easier to use with actual numbers. Let's say if the length of this first part of the segment is 2 and the length of the second part of the segment is 5. Segment addition postulate just allows us to add those together and say that the entire length is going to be 7. A little bit more complex if we just have algebraic expressions like we do on the next question rather than definite lengths. So let's try it with those. Let's say that EG is 59, and that gives us, again, the length of the entire segment from E to G. That entire thing is 59. We're going to use just these algebraic expressions to be able to figure out what's the length of both EF and FG individually, not just the length of the entire segment, which we already know. So if I'm trying to put that into a geometry expression first, I can use that segment addition postulate to say that if I add the first segment, EF, with the second segment, FG, I get that entire length, which again goes all the way from start to finish, from E to G. And now if I just substitute my algebraic expressions for those instead, the first one was 8x minus 14, the second one was 4x plus 1, and if I add those together, again, that entire length we know should be 59. Most of this, again, just going to be using your algebra steps. I want to combine my like terms and get 12x minus 13 on that left-hand side. We then want to isolate for our variable, so I get 12x to be 72. If I add that 13 to both sides, and then if I divide both sides by 12, I isolate finally and get that x is 6. In algebra, we'd be done, but we want to be careful that 6 is not our final answer. Again, what we want to do is we want to find those individual segment lengths and not just x. So what I want to do is I want to plug that answer back in. I know that if 6 is x, I can substitute for the first, substitute for the second. Sorry, that's not x. We know it's now 6. And it should be able to find each of those individual lengths. If I simplify the first part, 48 minus 14, we're going to get a 34 from that. And if I simplify the second part, 24 plus 1, we get 25. It's also good to check and just make sure that those individual segments added together should give us our entire length from E to G, which it looks like it does. 34 for EF, 25 for FG. That's going to add together to get 59 total for the segment. Next question, and works pretty similar, so it's a good one to try and see if you can do it yourself. add the first plus the second using our segment addition postulate. And we should eventually, again, isolate for x first. You want to use that to make an expression. If we get that x is 9, substitute that back in for both of those segments. We get that jk is 42, kl 78. And again, good way to check is to add those together, make sure that comes out to that total of 120. Next, we have differences in definition between equal and congruence. And again, you guys can read through this in a little bit more detail. I'm kind of brushing past this. A big thing that I want to point out again is notation. Notation can look like a small difference, but it means something important for these two different figures. If I say for something, for example, like I'm given two lengths that match, notice just like from before, we're using AB and CD without any kind of segment bar over it, like we would name a segment. So we're referring to those two lengths. So essentially all we're saying here is that if the lengths of two segments match with that 1 and the 1, that means those two segments are going to be what we call congruent. So I can say two things. I can say if the length of one segment is equal to the length of another. And if that's true, then that means the first segment is congruent to the second. So congruency essentially means equal, but it's specifically equal for a geometric figure. So I can say two segments are congruent, but I say their lengths are equal. Small difference, but that is an important difference. Next, if I'm looking for congruency, just like before, we could also just measure segments and decide if they're congruent. Congruency, again, we're looking for them to be the same length. Again, on a number line, oftentimes it's going to be easy enough to just count the length of AC, count the length of BD, and find that they're congruent. We could also go back and use our ruler postulate. If I find the absolute value of the difference from A to C, we're using those coordinates, so -2, difference of that in C looks like it's at 5, is going to be a difference of -7. The positive difference is going to be +7. And if I try that same thing going from B to D, honestly a good way to finding this also is just to use your largest number first. I know that D is at 10, I know that B is at 3, so if I just subtract that, I'm automatically going to end up with that positive difference. And if I see that those distances are the same, 7 and 7, just like we saw before in that last example, if the lengths match, so we call the lengths equal, we call the segments congruent. So I would say yes, AC and BD are congruent. Again, we would use marking like this. That congruency sign is like an equal sign with a little squiggly thing over the top. But yeah, I know they're congruent because those lengths, again, are equal. So lengths, again, equal. Segments, however, are not equal. We call those congruent. Trying that same thing with the next two segments, so A, B, and DE. Good thing to pause and try for yourself, but let's go ahead and reveal that answer. AB and DE should not end up congruent. It looks like AB is a length of 5, DE is a length of 4, so since the lengths are not equal, we find that those segments are therefore not congruent. So you do want to be careful about, again, equal congruency means something very similar, but lengths are equal, segments are congruent. Next, we have the difference between midpoint and a segment bisector. Again, you want to read through the definitions for both of those, but essentially the midpoint refers to just that point in the center which divides a segment in two equal parts. We denote those two equal parts with those matching congruency symbols. And the line itself, so again, this entire line would be what we call a segment bisector, whereas the point where it intersects, just that by itself is going to be the midpoint. Do want to make sure we can separate those two. We know what's the midpoint versus what's the segment bisector. The bisector is that entire piece that's cutting it, whereas the midpoint is just the point where it's cut. A good way to remember bisect as a term is like dissect in science when I'm cutting something open. I am cutting that line, and I'm also cutting it in two equal pieces, hence that term bisect for those two equal parts. So just like that last section, we can also use this to find some different algebraic answers. This time, all we're told is that Q is the midpoint of PR. Notice, unlike that last question, we don't know the entire length of PR first, but just by knowing that that's a midpoint, that should be enough to start with. If I know it's a midpoint, geometrically, we can make this expression, or this equation rather, PQ and QR should be equal. Again, that's going to be true because that was a midpoint, and that should be cut directly in half. So if I know they're equal, that means I'm going to be using this algebraic equation, 6x minus 7. My segment expression on the left should be equal to 5x plus 1, my segment expression on the right. And now, just like Algebra 1, we just got to make sure we can isolate this for x. I'm going to subtract 5x from both sides. Again, we want to make sure that only one side has x on it if I'm supposed to isolate. Add both sides, add 7 to both sides, and we get that x is 8 as my isolation. And kind of like with our last example, 8 is not our final answer. Instead, I want to make sure I take that 8 and substitute that back in. So if I'm trying to find PQ, I can take 8 and substitute that part in. 48 minus 7 looks like this first segment is going to be a length of 41. And actually, we don't necessarily have to plug in for our second piece. This is kind of revealing our second answer. We don't have to substitute x into our expression for QR because we know that PQ and QR are equal. Again, going back to the start of that question, so if I already found the halfway point and I know that halfway is 41, without having to substitute that back in, I know that QR is also going to be a length of 41. So you can use this as a sort of shortcut. If we know it's got to be a midpoint, we know if the first half is 41, that second half, without plugging that back in, is also going to be a 41. What we actually haven't found yet is the entire length of that segment. We're asked again for three things. We found PQ, we found QR. So PR is as simple as adding those together, or you can also just think multiplying one of them by 2. So if I'm looking for PR, I can just add those two, whoops, sorry, not plus. I can just add those two individual halves together, and that's just going to get me 82. Or again, you could just take half of it, that segment, and double it. So 41 was halfway, double that, I get the whole thing, which was 82. Very similar problem at the end, so you can just kind of test yourself and see if you understand that last concept. Again, we should be able to make this into an algebraic equation. Let's take a look at how that equation is solved here. How it's solved here. There we go. So again, I want to start by saying that PQ, or not PQ, TU and UV are now equal, just because we're told, again, this important point. If I wasn't told that, I wouldn't be able to start that equation. But if I know that that's a midpoint, I know exactly that I'm cutting that into two equal pieces. I could denote that with congruence if I wanted to. But the important part there is that we can set those two algebraic expressions equal to each other. Eventually isolate that for x, and we get that x is 3, or should have anyway. And remember, we don't necessarily need to substitute that into both expressions. We can just choose one of them to substitute. In this case, I substitute in for TU. And once I'm able to find one of those lengths, I know the other length is going to have to match. Otherwise, that wouldn't have been a midpoint. So 35 for the left-hand side, that's our TU segment. 35 for our right-hand side, that's our UV segment. And if I was to add both of those together, again, that's where my 70 comes from, is just by adding that and getting the length of the entire segment from start to finish. So a lot of algebra involved, but I think you can do it as long as you're able to do algebra 1.